Welcome. In this explainer, we are going to break down the core caching mechanisms that make MySQL's InnoDB engine so incredibly fast. We'll be looking at this from a solution architect's point of view, really digging into the secrets that help conquer disk slowness and deliver amazing speed.
Okay, let's just dive right in with a question that every single architect has to solve at some point. When you strip away all the complexity, what's the one thing, the single biggest physical barrier that's holding your database back?
And yeah, the answer, overwhelmingly, is the simple physical limitation of reading from and writing to a disk. I mean, it doesn't matter how fast your storage is, it is always going to be orders of magnitude slower than your system memory.
So that's really the battleground, right? Today, we're going to explore the really powerful caching tools InnoDB gives us to win this fight. We'll see how they all work together to build a high-performance system by basically doing one thing: avoiding that slow disk whenever humanly possible. All right, our first stop is the absolute foundation of this entire performance system, the InnoDB Buffer Pool. Seriously, getting this one component right is probably the most critical decision you're going to make. So think of the buffer pool as your database's short-term memory. It's this huge cache sitting in RAM where your table and index data can live. If a query needs data that's already in the pool, bam, it's served instantly. That's what we call a cache hit, and that is the key to speed.
And you know, this is the core game we're playing. A cache hit? That's a massive win. A cache miss, though, means we have to pay that slow, painful penalty of going all the way out to disk. The entire goal of performance tuning is just to maximize these hits.
And that's really the crucial point. A well-tuned system should be serving almost all of its reads directly from memory. If you're seeing a sustained hit rate over 99%, that's a great sign. It tells you your buffer pool is sized correctly for your application's working set, the data it actually uses all the time.
But what happens when one single large query comes along and threatens to ruin this perfectly tuned cache? Let's say a big analytical query, or maybe a backup job that has to read an entire table.
Now, a basic cache that just throws out the least recently used stuff would be an absolute disaster here. That massive query would just flood the buffer pool with a whole bunch of single-use data, and in the process, it would push out all of your valuable, frequently used hot data. Your performance would be totally destroyed until all that hot data gets read back in.
And here is the brilliant solution, a midpoint insertion strategy. Instead of just one simple list, InnoDB splits its cache. New data doesn't just get to jump to the front of the line. No, it gets placed in a kind of probationary zone, the old sublist. If it gets accessed again pretty quickly, okay, it gets promoted. But if not, it gets kicked out and it never gets a chance to disturb the truly important data.
And this slide just nails it with the nightclub analogy. The new sublist, that's the VIP section, where all the important data hangs out. The old sublist, that's the line outside. A big table scan might get you in the line, but you only get into the VIP section if you prove you're important by being needed again.
Okay, so our read cache is now fast and it's well protected. But that is only half the story. What about writes? They come with their own unique I/O challenges that can absolutely grind a system to a halt.
InnoDB's first tool for this is the change buffer. See, when you update a row, that often means you have to update multiple secondary indexes, which can trigger this messy storm of random disk I/O. So instead, InnoDB just kind of jots down a note about the change in this buffer. Then later on, it merges all those changes in one clean, efficient pass.
But this brings up a really critical challenge. If we're modifying data in memory and we're delaying the writes to the main data files, how do we guarantee durability? I mean, what happens if the server crashes before that data is actually written to disk?
The answer is the redo log, using a principle called write-ahead logging. And the accountant's journal is the perfect analogy here. Before a change is made permanent in the main books, it's first written down in a fast sequential log. If the power goes out, you can always rebuild the books from the journal. This gives us that durability without having to wait for those slow, random writes to the main data files.
And this log gives architects a really powerful tuning knob. By configuring how often the redo log is flushed to disk, you can explicitly trade absolute data safety for maximum performance. A setting of 1 is the safest, but it's also the slowest, while 0 and 2 offer huge performance gains, but at a calculated risk.
So far, pretty much everything we've talked about requires some manual tuning. But what if InnoDB could get faster all on its own? This is where it gets really interesting, with a feature that literally observes your workload and automatically boosts performance.
So InnoDB uses what are called B-tree indexes, and they're very efficient. But for super common lookups, where you're just looking for one specific thing, it can be even faster. So it monitors your queries, and for the index pages you access all the time, it builds a hash index, a shortcut, right there in memory. This turns a multi-step tree search into a nearly instantaneous direct pointer lookup. It's awesome.
So as an architect, how do you put all this stuff together? Well, it is not about just turning every knob to the max. It is all about understanding the trade-offs and configuring the system for your specific workload.
Take that adaptive hash index we just talked about. It's fantastic for read-heavy workloads, but under really intense high concurrency writes, the cost of keeping that hash index updated can actually create a bottleneck. You get what's called lock contention. It's like having too many people trying to update the same whiteboard at once. In that case, it can actually slow the system down, which is when you'd want to turn the feature off.
It's the same thing with checkpointing. That's the process of flushing modified data from the buffer pool to disk. It is a constant trade-off. Frequent checkpoints mean if the server crashes, recovery is going to be super fast, but all that constant I/O can limit your peak performance. Infrequent checkpoints, on the other hand, allow for higher throughput, but at the cost of much longer recovery times.
And even when you have a perfectly tuned system, architects always have to plan for restarts. A cold start with a totally empty buffer pool can absolutely cripple your application's performance. For the first few minutes, almost every single query is a cache miss, leading to a storm of disk I/O and response times that can be 10, even 100 times slower than normal.
And that really is the key takeaway here. The buffer pool, the change buffer, the redo log, the adaptive hash index, they are not magic. They are a set of interlocking tools, and each one has its own trade-offs. They're designed to be configured by an architect who understands their application's specific needs.
So, as we wrap up, just remember that it is not enough for these powerful features just to be turned on. An unexamined default configuration might actually be working against you, which leads us to the final, critical question you should be asking about your own systems.